Okay, students, I do apologize profusely that this video is late, but I was out of the country for spring break and I was just jet lagged, honestly, and I just have been having a hard time recovering from that trip. So, here we go, Chapter 6, Quantum Theory and Electronic Structure of Atoms. A lot of this material is very, very heavy in the math, and we are not going to do that heavy math. We're going to gloss over it because the more important, Chapter 6 and 7 very much go together. And some of the more important material is in Chapter 7, and it's very hard to get your mind around anyway without doing that super heavy math. So we're going to discuss it but not do the math. Okay, here are your topics that we're going to be discussing. We're going to try to make it through the first 4 sections in this video tonight. The first section talks about the properties of waves, and those are important. You all did a flame test lab, and so that has a lot to do with this particular chapter, the electromagnetic spectrum. And that double slit experiment is one that went towards showing the photoelectric effect and how these particles can act like waves and particles as well. So let's talk about the nature of light. Okay, when we talk about light, we're talking about the light that we can see. That's what we generally think about. Visible light, light that has color. However, visible light is really only a very small part of what's called the electromagnetic spectrum, and that is all the energy that we get from our sun. Everything from down here at the very bottom, radio waves that have very, very low energy, to the very far end of this, gamma rays, which have extremely high energy, and everything in between. But the truth is, visible light, which is somewhere in the middle, kind of towards the lower half of the middle, visible light that we see with color is only a very small portion of all of this spectrum. These are the colors red, orange, yellow that we see, that we think of when we say light. This is what we actually see. So this encompasses what we call the electromagnetic spectrum. And when we talk about waves or energy, this is what we're talking about. So get that in your mind. Okay, and since this energy comes to us in the form of waves, just like ocean waves or sound waves travel to us differently than ocean waves, but we need to talk about wave crests. This is the crest, and here's the trough, and the distance between one crest and another crest, this is called a wavelength, and it is denoted with the Greek letter lambda. This upside down Y looking thing is the Greek letter lambda. It's drawn just like you would draw an upside down Y. That's the Greek letter lambda. Then, if you were to draw an imaginary line through the middle of this wave, from the middle of a crest, the top of a wave, down to the bottom of a trough, the distance between halfway up is called the amplitude, or the height of the wave. Okay? So a wavelength is crest to crest or trough to trough, and then the amplitude is the height midway between the crest and the trough. That's your amplitude. Okay, so you got that? And then frequency. When you think of frequency, what I want you to think of is, and it's denoted with the Greek letter nu, which looks like a V. It's how many waves can pass a given point. Like you put a point on here and you let that be your starting point, and let's count how many of these waves can pass that point in 1 second. That's frequency. And the way I think of wavelength and frequency is a dog walker. So I want you to think of a dog walker with me in New York at Central Park. And they make a lot of money, by the way. So they have all different kinds of dogs. And let's take this dog walker, imaginary dog walker, and they're only walking 2 dogs today. They're walking a Great Dane and they're walking a Chihuahua at the exact same time on leashes that are the same length. Think about that with me for a moment of your time. If you have a dog walker, here's your dog walker right here. You can see my beautiful drawing. Here's his hat or her hat, and here's the leash, and 2 identical leashes, but one is holding a Chihuahua and the other a Great Dane. Now those dogs are going to be walking the same speed, the exact same speed. They're both pulling that dog walker through Central Park. And if you don't think that Chihuahua is going to be trying to keep up with that Great Dane, you don't know Chihuahuas very well. Because he is going to be keeping up with that Great Dane and trying to pull ahead, as a matter of fact. So they're going to be pulling on that same leash. It's going to be taut. But who is going to have to take more steps? Okay? The number of steps that dog has to take, you can think about that as being frequency. How long the step is, think about that as wavelength. Okay? So the little Chihuahua, he's not going to take but a step that big, so he's going to have to take many, many, many steps. Here's the Great Dane's stride, perhaps. So look how many steps the Chihuahua is going to have to take for every 1 step that the Great Dane makes. Mind you, they're going the same speed. They're both pulling on that dog walker for all they're worth. But that Chihuahua's feet are really getting it. And that Great Dane is just moseying along. Even though they're going the same speed, that Great Dane doesn't have to take as many steps. That's frequency. Think about that. Okay? The number of waves that pass a particular point in 1 second. That Chihuahua has to take many more steps, or many more frequency, many more waves would have to pass by. So he has a lot more energy being expended. Okay? That's what I want you to think of. We already discussed what amplitude is, the vertical height of that wave. All right. So think about that with me. Now, here's where we're going to get this. Since those waves are all traveling with the exact same speed, and that is the speed of light, and the speed of light in a vacuum is she uses the 2.9979. I've always rounded it to 3.0 times 10 to the 8th meters per second. That is the speed which all light travels. It's constant. Einstein said that. The speed of light is constant in a vacuum. And so that speed of light is going to be equal to the wavelength, how long is that wave, times how many waves are going to pass that point. If you relate this to the Great Dane and the Chihuahua, it makes sense. Their speed that they're traveling at is going to be how long their stride is times the number of steps they have to take. That's what you can think about it as. So the longer this is, the fewer the number of steps they have to take. In the Chihuahua's case, since he has a really short step, he has to take lots of steps since his short stride wavelength. All right. What you do need to know is that in the term of light, that long wavelengths usually mean low energy, and short wavelengths, think about the Chihuahua, high energy, because they're really making a lot of those crests are passing that point in a given period of time. Okay, so here's a problem that is in your textbook, sample problem 6.1. What type of laser that's used in the treatment of skin lesions is a neodymium doped yttrium aluminum garnet laser. This wavelength that used to treatment is 532 nanometers. What's the frequency of this? Well, a nanometer is a billionth times 10 to the negative 9, that is. What's the frequency? So you're going to use this formula, same formula, C is equal to lambda times nu. Okay, this is your 2.9979 times 10 to the 8 meters per second. There's your lambda, and this tells you what your wavelength is right there, and that's in nanometers. Okay, and so 1 nanometer is 10 to the 9th meters, so you have to change that into meters since your speed of light is in meters. So that's what you're going to have to do first. You're just changing nanometers to meters. You have to do that because your C is in meters. It's 2.9979 whatever times 10 to the 8th meters per second. Remember that from a few slides ago? Okay, and so then to find, since C is equal to lambda times nu, if we want this V by itself, you have to divide by lambda. So then you have, she rounded it now to 3.0 times 10 to the 8th, speed of light. C is the speed of light, so that's 3.0 times 10 to the 8th meters per second, divided by your wavelength changed into meters, and that meter takes out that meter, and that leaves you, when you do that math, please remember, when you put this in your calculator, I've said it before on a previous video, when you put this into your calculator, please remember to enter in your 3.0. Use this second and that comma right here, right above that 7. That's your EE, your exponent button. And you can see on the calculator it puts an E there for you. And 8. And then divided by your 5.32. Then you use your second button again and your EE button, which is the comma right above your 7. And go ahead and then put your negative 7. If you don't do that, then you're going to get an incorrect answer, or you need to be sure to use parentheses, okay? And you can see there you get 5.64 times 10 to the 14th. And it's seconds is on the bottom, which is why you have this little negative 1 up here, because seconds is in the denominator. And that is a hertz, by the way. Okay, this is the unit for hertz. Frequency is measured in hertz. All right, and so this is the electromagnetic spectrum that I drew for you a little while ago. They drew it opposite what I did. They put the highest energy to the left and the lowest energy to the right, where I went the other way for you. But again, if this is your electromagnetic spectrum, all the energy that we get from the sun, you only get to see this amount. And then you have your very long wavelength radio waves. That means low energy, very long. And then your very short wavelength That means very high energy gamma rays, X-rays, ultraviolet, infrared, okay, and so on. Those are in your textbook for you. All right. Let's see why we care about these and what in the world they have to do with chemistry. Okay? When you take anything and you heat it, it does emit radiation, and that's called black body radiation. And it does so over a wide range of wavelengths, okay, from short to long wavelengths. And so there have been lots of attempts, and by the way, this is how scientists are able to tell what elements are in stars, whether stars are coming toward us or away from us, by studying the radiation that they emit. And so a scientist called Planck, many years ago, he developed a model that said that you could measure the amount of energy in discrete quantities. He called them bundles. He called these bundles, and he was named, he's given Planck's constant. A constant was named for him because of that. And he called this quantum, the amount of energy that could be measured, okay, that could be given off or absorbed by electromagnetic radiation. And so we have this formula. The amount of energy, this H is Planck's constant. And then you have your nu, your frequency. And H is your Planck's constant again, and it is Planck's constant. I would not ask you to memorize that. You don't have to. 6.63 times 10 to the negative 34 joules seconds. Okay? And then we have Einstein's very, very famous, changed the world famous, photoelectric effect. Everybody thinks he got the Nobel Prize for his work on gravity, but he did not. He got the Nobel Prize for this, photons and the photoelectric effect. He noticed that when electrons hit certain metals and they reflect those, that they act a certain way, okay? And the way that they get reflected could not be explained if those electrons are said to only act as particles or only act as waves. And so he pondered why that could be, and he came up with his idea of the photoelectric effect, and that led to so many of the ideas and theories that we have today, and it has been upheld by all the experimentation that has been done, and it led to an entire branch of chemistry and physics known as quantum physics and quantum chemistry that changed our world, completely changed our world. Lasers, the atomic bomb, everything as we know, just from the idea of, hey, light can act as either a particle, like you're throwing a ball so it can go into a straight line, or it can sometimes act as a wave. Okay? And all of that came from the idea of photoelectric effect. So, photons and the photoelectric effect. This is what Einstein said. He made this extraordinary assumption. He said that light could act as a beam of particles, like you were throwing a ball, so they could go in a straight line. And he called these photons. Okay, he didn't call them, we now call them photons. So when you think of Star Trek and photon torpedoes and everything, those words came from somewhere. They weren't just made up. They came from this kind of theory, the quantum theory. And so then, now we have the energy of a photon is equal to Planck's constant times the frequency. of whatever light, and we can measure that. We can actually measure that. And I'm sparing you the problem in the textbook, the sample problem, where they actually do that and asks you how much more energy is given off from a green light than red light, or things like that. And if you wish to explore that and do that sample problem, you're more than welcome to do so. Okay, but this is what is more important to me. It says if the frequency of the photons exactly equals the energy, then the light is going to have just enough energy to knock those electrons loose. And that's super important, because that is what leads to the release of energy, giving off light, bonding, all kinds of things that we're going to study. All right? Now this right here in section 3 is all in color in your textbook, and it's really pretty. And I can't make my video thing work today, so that's why we're doing it this way. But here's the emission spectra of atoms that can be used to identify them. That is going to be super cool in your textbook. Again, I was telling you that this is what is used to identify elements that are in planets, that are to tell whether planets are coming toward us or going away from us, and that specific wavelengths, so they're just like a fingerprint for elements. So here's the atomic line spectra. Here's a little slit and a prism, and here is a charged tube that's got a particular element in it, and so it's allowed to go through this slit, through a prism, and it gives you this beautiful line spectrum that is just like a fingerprint. And you can measure its wavelength in nanometers, and then you can identify what element that it is based on its atomic spectra. And you can have, there are periodic tables that are built just by the atomic line spectras. And if you can look through a spectrophotometer, here is the hydrogen atom, and here lithium, sodium, all of these. Here's hydrogen's line spectra, and again, it's totally awesome, just like a fingerprint. Can be used to identify elements that are in planets. This is how they know. All right. According to classical physics, an electron that's moving in an orbit of hydrogen would radiate away energy in the form of electromagnetic waves. Therefore, an electron would quickly spiral into the nucleus and it would annihilate itself. That's what it used to be thought of. Okay, that's how it used to be thought. But then Bohr, Niels Bohr, said that hydrogen allowed to occupy only certain orbits because they had certain energies, and so they couldn't do that. So that these electrons had a fixed amount of energy, and so they couldn't just spiral down in. So that these electrons would not be allowed just in any old orbit. They had these certain amount of energy, and so they would be in this fixed orbital state, and there it would stay. So it wouldn't spiral down in. And here he even postulated how much energy that it would be, and he called that energy its ground state. Okay, the lowest energy state that an atom that's not excited would have, that the electrons in that atom would have. Like if you had sodium, for example, you had its protons and neutrons in the nucleus, and then you had its electrons in its energy levels, 2 here, 8 here, and then 1 in its third energy level. He could quantize and calculate how much energy these electrons had, and those electrons, when they were in their proper orbitals, he called that the ground state, the lowest energy state of an atom. Now, when you all did your flame test and you heated those, You excited these electrons, gave them some energy in the form of heat from a flame. So you excited them and took them out of their ground state and rose them into higher states. And they couldn't stay there, though, because they innately belong in this particular energy level. So when you gave them that extra energy, they flew up to a new energy level, but they couldn't stay there for very long. It'd be like some, basketball player having a really good day, moving up to the pros. For a little while, he might be able to hang, but he can't stay there if he's not ready. So he falls back down to where he belongs at the high school or collegiate level until he's ready. Ground state, in his ground state. That's kind of what you can liken it to. And so when it falls back down where its ground state is, it releases that energy, and we see that energy, or you saw that energy, in the form of light. Okay, that's what it's talking about. That was called the excited state when you heated it, and when it dropped back down, it's called the ground state. And you can actually calculate how much that is. And I'm not going to ask us to do that again because this is so difficult as it is. But this is what happens, called the Balmer series and the Lyman series. And it shows you how when you give it extra energy, it will fall back down to where it belongs. Now, I think that's enough for tonight. I will give you some homework and let you have it.